Welcome back, everybody. I'm going to show you a couple more examples of hypothesis testing involving two population proportions. And of course, these examples will involve only the p-value method, not showing all 5 steps of the critical value method. Here's how the first one reads. The Joint Commission on Accreditation of Healthcare Organizations mandated that hospitals ban smoking by 1994. In a study of the effects of this ban, subjects who smoke were randomly selected from two different populations. Among 843 smoking employees of hospitals with a smoking ban, 56 quit smoking 1 year after the ban. Among 703 smoking employees from workplaces without a smoking ban, 27 quit smoking a year after the ban. Is there a significant difference between the two proportions at the 5% significance level? We will demonstrate the p-value method. First of all, we're going to set up the hypotheses that we're going to be testing here. The null hypothesis says that population 1 proportion is equal to population 2 proportion. The alternative hypothesis says that these population proportions are not equivalent to each other. Now, since it's a two-tailed test, it really does not matter which one you designate as population 1 versus population 2, because your decision would be the same regardless of your choice, because you do have two rejection regions. When you conduct a one-tailed test, a lower or upper tail test, you have to be a little bit more careful as to which one you designate as being population 1 versus population 2. Okay. All right. So for this example here, we're going to test these hypotheses here. I'm going to designate population 1 as being those that, employees that worked for a company that did implement a smoking ban. And population 2 will be consisting of employees that did not have a population ban in effect. Okay, so therefore our X sub 1 is going to be the number of employees who did quit smoking that did work for a company that had a population or a hospital rather that had a smoking ban, and that was 56 that did quit. And the sample size one would be 843. So 843 employees were randomly surveyed. Now, for hospital number 2 or population number 2, involving employees that worked at hospitals that did not have a smoking ban, we've seen that 27 quit smoking 1 year after the ban, and we see that 703 were randomly surveyed. So these are the numbers that are going to go into the calculator for the 2-prop z-test function in order to conduct this hypothesis. These examples, by the way, that I'm going over right now are found on the dashboard of Canvas in the link entitled Online Examples. So you might want to go there first and print these out and follow along here. Okay, so let's conduct this hypothesis test using the calculator. So what you do is you hit your stat button, you go over to test, you go down and grab the 2-prop z-test function, 2-prop z-test, and then you just have to type in the numbers that we designated. So X sub 1 will be 56. N sub 1 is 843. X sub 2 is 27. N sub 2 is 703. This is, again, a two-tailed test because we have the not equal to symbol for the alternative hypothesis statement. Go down to calculate. We're ready to crank this out. Here we go. All right. Your test statistic for this test would be 2.434 about, and your p-value is 0.015. Now notice we tested at 5% here. And so notice your p-value, which is 0.015, is less than 0.05. So your p-value is less than your level of significance alpha. And when your p-value is less than alpha, we always reject the null hypothesis. And therefore, ladies and gentlemen, sample evidence is strong enough to suggest that we are going to reject the null hypothesis, and therefore it looks like the claim is being supported by sample evidence here. That indicates that there is a significant difference between the two proportions of smokers who did indeed quit 1 year after the ban. So it looks like the proportion of smokers that quit 1 year after the ban is not equal to the proportion of smokers that quit that worked for hospitals that did not have a ban. So that concludes this test using the p-value method. Whenever we conduct a hypothesis test involving two population proportions, you can always also construct confidence intervals for the difference between the population proportions. And so that's the next thing we're going to do now is construct a 95% confidence interval for the difference in the population proportion of subjects who did quit smoking after the ban. Okay, so to build this 95% confidence interval, we would go to our calculator and we then hit our stat button and we go over to tests. And then we're going to go down till we grab the, let's see here. Whoops, excuse me. Yeah, here it is right here. It's the 2PROP-Z-int function, the proportion Z interval function. So therefore, let's now dive into this function here. X sub 1, N sub 1, X sub 2, N sub 2 are going to be the same as they were when we conducted the hypothesis test. So notice those values are the same. We're not going to change those values. So we just go down and establish our level of significance, which is 95% or 0.95 as a decimal. Go down to calculate, and here we go. We're ready to build a confidence interval. All right, so that is our confidence interval here, which has a lower end point of 0.006 and an upper end point of 0.050. Okay. Now, ladies and gentlemen, this is of critical importance here. Notice that both endpoints of this confidence interval are positive. And if you think of the real number line, if you have two positive numbers on a real number line, 0 would not be a number in between two positive numbers. 0 would be found in between a negative value for a lower endpoint and a positive value for an upper endpoint. And because both these endpoints are positive, that would suggest that there is a significant difference between population 1's proportion versus population 2's proportion. Okay. Specifically, this confidence interval is saying this, that P sub 1 minus P sub 2, population 1's proportion minus population 2's proportion, is in the confidence interval whose lower endpoint is 0.00601 and the upper endpoint of which is 0.05003. And again, ladies and gentlemen, notice these endpoints of this confidence interval are both positive. That would suggest that the difference between these population proportions is greater than 0, meaning it is positive, because the endpoints of the confidence interval are positive. So that being said, this is saying then that population 1's proportion is greater than population 2's proportion. That's what this confidence interval is saying, and we're 95% confident or certain in saying such a thing here. Okay. Now, if we built a 95% confidence interval for the difference between population proportions, and we found out that the lower end point of the confidence interval is a negative number, and the upper end point is a positive number, then we would say that 0 would be a value that would be found in this confidence interval, since 0 lies between a negative and a positive number on the real number line. So in this case, if we did get a confidence interval that was built like this, we would say that the difference between the population proportions is essentially equal to 0, which means or would imply that the population proportions are equivalent to each other. But we didn't get that. Since our confidence interval has both positive endpoints, again, we would say that population 1's proportion exceeds that of population 2's proportion. So the nice thing about confidence intervals is they give us a more pointed idea as to which proportion is superior versus inferior, whereas this hypothesis test up here was just a non-directional test and just indicating whether the proportions are equal to each other or not equal to each other. There's no way from the hypothesis test you can gather, just by saying that the population proportions are not equal to each other, which one is greater or which one is smaller. And that's why confidence intervals give us a little bit more information regarding the unknown population proportions here. Okay. So it does look like the proportion of smokers who quit 1 year after the ban was larger for employees that worked in hospitals that did have a ban in effect versus hospitals that did not have a smoking ban in effect. Okay. All right, one last example here. This is an example of an upper tail test, a hypothesis test involving 2 population proportions. And this is how it reads. The drug Clarinex is used to treat symptoms from allergies. In a clinical trial of this drug, 2.1% of the 1,655 treated subjects experienced fatigue. Among the 1,652 subjects given placebos, which are non-medicated pills, 1.2% experienced fatigue based on data from the Schering Corporation. Use the 5% significant level to test the claim that the incidence of fatigue is greater among those who use the Clarinex drug. All right, so this is definitely going to be an upper tail test. So we first of all establish our hypotheses that we're going to test. Our alternative hypothesis is saying that the proportion of people that use the proportion of people that experience fatigue rather while using the drug Clarinex is greater than the proportion of people who did not proportion of people that did experience fatigue that did not use the drug Clarinex. The null hypothesis would say that these population proportions are equivalent to each other. And so, ladies and gentlemen, since I've established my hypotheses this way, population 1 is going to be those patients that did use the drug Clarinex, versus population 2 are going to be the patients that did not use the drug Clarinex or use just the placebo or non-medicated pill. Okay, so therefore we need to determine what x sub 1 is and n sub 1 is, and what x sub 2 and n sub 2 are. Well, x sub 1 is going to be the number of patients of those surveyed that used Clarinex that did experience fatigue, and it said that 2.1% of the 1,655 patients that used the drug Clarinex did experience fatigue. So x sub 1 is going to be 2.1% of 1,655. Now, ladies and gentlemen, it's critical that when you use the 2-prop-z test, or you build a confidence interval for the difference between proportions, it's very important that x sub 1 and x sub 2 be integers. They cannot be decimals. So here we go. To find x sub 1, we're going to have to take 2.1% of 1,655, which means we turn the percent into a decimal by shifting the decimal point 2 places to the left, dropping the percent symbol. So that's going to be 0.021. Then we're going to multiply this by our sample size, number 1, which is 1,655 patients. So let's get on the calculator and dial that up. So that's 0.021 times 1,655. Now I get 34.755, But ladies and gentlemen, remember, x sub 1 and x sub 2 cannot be decimals, or else your function will fail or will just basically die on your calculator. So I'm going to bump this 34.755 up to 35. Let's call it 35. Sample 1, of course, is going to be the 1,655. Now, of the 1,652 patients that did not use the drug Clarinex, 1.2% of them experienced fatigue. So x sub 2 is going to be 1.2% of 1652, which means we take 0.012 and multiply it by 1652. Okay, and when we do that, we get 19.824. But again, you cannot have decimals. And so we're going to round that 19.824 up to 20. Let's just call it 20. And n sub 2, of course, is 1652. Okay, ladies and gentlemen, we're going to take these numbers now to the 2-prop z test function to actually conduct this hypothesis test. So go to your calculator, hit your stat button, go over to tests, go down and grab the 2-prop z test function. Now for x sub 1, we're going to type in 35. N sub 1, 1655. X sub 2 takes on the value of 20, and n sub 2 takes on the value of 1652. This is a upper tail test. Notice, because we got the greater than symbol, that is the alternative hypothesis statement. So make sure you select the greater than. Hit enter, go down to calculate. We're ready to conduct this test. So here we go. Boom. Your test statistic would be the 2.032 blah, blah, blah number. Your p-value is 0.021. Remember, we were testing at what percent? We were testing at 5%. So notice 0.021 is a little less than 5%, 0.05. Being the case, the p-value being less than alpha, we would reject the null hypothesis. And so therefore, ladies and gentlemen, we're going to reject the null hypothesis. And because we're rejecting the null hypothesis, sample evidence is strong enough to suggest that the claim is being supported. The claim being that the proportion of patients that suffer from headache is greater for those that take the drug Clarinex as opposed to those that do not take the drug of Clarinex. And we only stand a 5% chance of committing a type 1 error and rejecting the null hypothesis that may in fact be a true statement. So that's the p-value method to illustrate this hypothesis test involving 2 population proportions here. Now we will, for this same example, come down here and build a 95% confidence interval for the difference in the population proportions. So, in other words, we're going to try to find out in what interval p sub 1 minus p sub 2 lies in. So to build this confidence interval, notice your x sub 1, n sub 1, x sub 2, n sub 2 values remain the same. So all you have to do to build this confidence interval again is just clear your screen, hit your stat button, go over to test, go down to go down to 2-prop z int function, the 2 proportion z interval function, hit enter. Notice x sub 1, n sub 1, x sub 2, n sub 2 are all the same. Don't change those, just go down. Make sure your constant confidence level is 0.95, 95%, and we're ready to build our confidence interval. Hit calculate, and there it is. That is your confidence interval here. Now, notice the lower end point of your confidence interval is 3.3 times 10 to the negative 4th power. The bottom line is that's a small number, but it is a positive number. And so you can see, ladies and gentlemen, that our lower end point of this confidence interval is a positive number, and the upper end point is also positive. And since both the endpoints of this confidence interval are positive, we can see that p sub 1 minus p sub 2 is indeed also a positive value. which implies that P sub 1 is greater than P sub 2. And notice this confidence interval supports our conclusion we arrived at when conducting the hypothesis test above here, that the proportion of patients that suffer from fatigue that use the drug Clarinex is greater than the proportion of patients that suffer from fatigue of those that do not use the drug Clarinex. So you can see that both these methods corroborate or support each other. So we're 95% confident that the difference between these population proportions belongs to the confidence interval, which has a lower endpoint again of 0.00033, and the upper endpoint is 0.01775. And we're 90% certain that the difference of these population proportions is indeed a value that lies between these two positive values here. So these two examples show us how, again, to do the p-value method in conducting a hypothesis test for two population proportions. And it also shows us how to build confidence intervals for the difference between population proportions. After having viewed these examples and reading section 11.1 in your textbook, ladies and gentlemen, you should be ready for the textbook homework and also the homework problems on MLP. So you should be all set. I hope everybody's okay. Hopefully you're all staying healthy, and please try to keep up with the schedule and always be conscious of when things are due. If you ever have any questions on anything, please let me know, and I'll be more than happy to help you out to the best of my ability. Take care.